Good afternoon, everyone. I don't think any more people will probably come in now, so I think we can begin. Can you hear me? It's fine? Okay, cool. So, thank you very much for coming. My name is Alberto Revelli. He's Nico Neiddecker. And today we're going to talk about DNS tunneling, as you probably have noticed. A little bit about us. We work for Porcalis Computer Security. It's a London-based company doing penetration tests and forensic analysis services. Personally, I'm the technical director of the Italian chapter of OWASP. I contributed in writing the OWASP testing guide 2.0. And some of you might know me through SQL Ninja, SQL Injection Toolkit.
Yeah, I'm from the same company. Actually, we work together. I'm not technical director of anything, unfortunately, but I did some research in low-level protocol security. Nothing significant, really. But we had to fill that slide, so this is who I am. I do bug hunting occasionally and a lot of coding, actually.
So, a little bit of what are we going through. First of all, we'll just give a little bit of overview what it's all about why we are interested in DNS tunneling, what we can get out of it. Then we will talk about a little bit the state of the art, the existing tool, existing technologies.
We're just need you in here a little bit. All right. So that way I don't have to change the camera.
Am I not enough?
No, you're good. This will be good.
Okay. So we will see, after analyzing a little bit the existing tool, existing technologies, we will see how to make the tunnel faster, first of all, and possibly also harder to detect from an IDS or an IPS. Then we will see a little bit of all the troubles we run into while trying to achieve those two goals. We will have a quick demo of the concept we've implemented, and finally we'll just go through like the key takeaways of what we learned from these and possible future improvements. So, what are we talking about? The situation is pretty much there is an internal host in a LAN, there is an external host. We want to have those two boxes to communicate in some way, even if the firewall in between doesn't want us to. We want this communication to be reasonably fast, maybe not incredibly fast, but at least reasonably fast. And we also want to be able to hide the fact there is a communication going on between the two boxes. There are various scenarios here that come to mind. You might be a penetration tester. You were able to exploit some machine in the internal network, have it run your code. Now you want that machine to call you back somehow and have a reliable communication channel. Or maybe you're just in an airport lounge or in a hotel room. They give you internet for an astounding amount of money. You don't feel like paying it, so you want to be able to sneak your way out of the internet. And finally, the one which I think is the most interesting scenario is if you happen to be a corporate spy, or if you want to defend against a corporate spy that is after you trying to steal all documents, all Excel files from all the laptops in your network through a custom Trojan that is going to have your people to download. So there are various scenarios that we can think about. In all cases, we want to create some covered communication channel. The simplest case, I'm quickly going through this. Of course, the internal host, the agent on the internal host could just start looking for an open port on the firewall, a port that is allowed through, and then just start use netcat or SSH on it and just start sending out data. This is easy, not very interesting. It gets a little bit easier if you find that some protocol is allowed, but not the protocol you're interested into. So at this point, what you're interested in is to tunnel the first protocol into the second. So for instance, let's say that ICMP is allowed to the firewall, and we know that an ICMP packet looks pretty much like this. You have space phone data. What you put in there, you just put another IP header containing your protocol, and you start passing that back and forth. This is slightly more interesting, but there's, again, massive amount of research on these already, tools, everything. The really interesting case is when there's no possible communication between the internal host and external host. Or to be more precise, there's no possible direct communication. The only way to actually exfiltrate that data at this point is to use some third machine that actually can be used as a proxy, and we can piggyback on it in order to bring our traffic outside. And we have lots of potential alternatives here. The most straightforward one is to look for an HTTP proxy. You just scan the network for port 8080 or 3128, and then just create your HTTP request in which you encapsulate your data, run over it, wait for the response, and that actually works quite well. The problem is that the proxy might be authenticated, and you might not have the proper credentials in order to that. It might be that the machine you exploited actually has already stored credentials for the proxies. But what can happen is that maybe the process that your agent has is actually runs under a different user. That makes things harder because you would see the Windows register as a different user at that point. It would be kind of tricky to retrieve those credentials. And finally, proxy requests are likely to be logged, so it's not it's not very sneaky approach, in my opinion. Pretty much similar considerations for email. It's very easy to find an SMTP server. Just see if you can send a mail to arbitrary domains, build up an email with your data and send it over. Again, the problem is that also the server might be authenticated, so same problem as before. The communication would be relatively slow because, of course, you need to wait for the email to be delivered to your box. The channel would only be half duplex. You can send email out, but it's hard to respond to those email unless your agent can read emails sent to some local users. And also, mails can be individually logged. You can encrypt them, of course. You can make it hard to understand what is inside, but the emails are going to be there. It's going to be quite visible. So that's why we thought that DNS is the most interesting approach. Internal hosts are almost always authorized to resolve external names. In our lives as pen tester, it's been a very, very rare case in which internal hosts were not allowed to resolve external domains. DNS requests are not likely to be individually logged. The DNS servers are already there. They're already set up in any networked machine, so we don't have to look for one to use. The problem is that we don't have much space in the packet, especially for the upstream data. And also another problem is that, well, your IP need to be an authoritative IP address for the domain, but that's very easy to do. I mean, just a very tiny investment. And the way it works, in a nutshell, basically, you make the internal host take your data that you want to exfiltrate, build up a host name with it, and call NSLOOKUP, for instance, to the local DNS server. The DNS server will ask .com DNS server who is authoritative for evil.com. It will get the answer that XYWZ is authoritative, and then the request will be passed on to our box, and we will receive our data. We take the domain name, we just decode it, and we just have our data. For the downstream data, it's pretty much straightforward at this point. We had the request, we just send a response on the other direction. For instance, in this case, we have a TXT query request, so we send back the data to the DNS server. The DNS server receives the request, pass it back to the internal host, which receives the downstream data. So we have a full duplex communication. Nothing new so far. There are plenty of tools that do this. Ozyman DNS by Dan Kaminsky. Hey there. Iodine, DNS to TCP, NSTX, Squeeza is one of the most recent one, very interesting tool too. Also SQL Ninja does that, but in a very simplified way at the moment. It just creates a half duplex channel because in order to send data there, we still have the SQL injection application that does it for us, so it's a very stripped down version of it. So we're starting from here. Now what? The problem is that, again, DNS packets do not allow much data to be stored into them. And this might be a problem if we want to transfer lots of data, like in the corporate espionage scenario, or if you want a decent bandwidth, if we're not just interested in like a shell or a meterpreter payload, but we want, for instance, to open up an RDP or VNC connection to have actually graphical access. Also, another problem is the fact that DNS tunnel generates a massive amount of DNS requests in order to transfer a significant amount of data. So detecting and pinpointing such the machine that is responsible for that traffic, it's not a hard task to do. So in our spare time, we thought, okay, let's see if we can partially solve those problems. And so the first point was to make the tunnel faster, and Nico is going to talk about that a little bit.
Okay. Yeah, do you want?
Yeah, go ahead.
As we know, probably, or most of you know anyway, how DNS names look like and how much space there's left or available for us to use. These are actually only 253 characters, excluding the domain name. And the 253 characters are split into labels, which are maximum 63 characters long. And from the RFC, the actual original RFC, there's 1034. We can only use alphanumerics, which is case insensitive, so A to Z and 1 to 9 and hyphen. If we look for the example domain evil.com, how much space we actually have left, it's just not much. It's not much. In this case, 241 characters. Every character can have a value of one of 37 values. Yeah. There's something in the RFC. If you read those RFC, it says that you can request multiple host names in one request, which is in the RFC, but it has never been implemented in any of the name server softwares we looked at, which is unfortunate because this would be something really, really helpful. We can't use it though. For the data now, we have to think that if we tunnel RDP session, we don't have the data, the way it looks like is arbitrary basically. It's binary data. It's from values from 0 to 255. And in order to transport it via DNS, we have to encode it in preferably base 32 because we have an alphabet of 32 characters, which is pretty close to our 37. The problem with base 32, or well, if we encode something, is that in effect, we end up with a less payload data, or actually use data because we have to encode it. We widen it, we spread it basically. We're out of 8-bit byte characters, we made 5-bit byte characters in base 32. Which ends up, in the example before, 241 times 5 bits, which we can transport in each packet. There's roughly about 150 bytes, maybe, more or less. That's not very good. And even if you gzip it or anything, it wouldn't get much better. This is one example. This is Dan's baby, Oziman. Where we can see the stump, this is actually base 32 encoded data transported over the layer. Yeah, that is how it is today at the moment. Now, we went back and read a couple of more RFCs, and actually we discovered 2 sections, or 2 RFCs, quite interesting, which state that we actually can use arbitrary data in our DNS names, no matter how they look like, just how the data is from the complete 8-bit bytes, basically. It says it down there. There are 8-bit bytes and all values are allowed, which is RFC 4343, which is great, which means before we could tunnel 150 bytes roughly base 32 encoded, which means we could potentially tunnel 100 bytes more each request, which is a great effort, something really good we can use. The problem with that is now there are library functions which we can use in order to send over requests, like get host by name, probably everybody knows. The problem is if we write a tool in C, we have to take into consideration that strings are terminated by null. So if we send, or if we construct a DNS request with a null byte in it, this would be it. We can't just send requests with a null byte in it. Yeah. Well, the thing now is though, if we look how the domain names are actually constructed in a raw header, we can see it looks basically like this. We have we have 1 byte before each label, which states how long a label is going to be. Then the label data, which is here 63 chars. Another label, another byte indicating the length of the labels, and this is going until we reach a 0 byte. The good thing now is, or if you look how those data would be processed, you see that domain name, or the servers actually, they don't care how the labels look like. They read the length field and then they do something with the label or don't. So we can put null bytes into the labels how we like, or any other character. It's just important that the labels say what they say, how long the label is. Sorry, the label length say how long the label is. Which means we tested it. We tested it using bind9. We wrote a little program which would construct a binary data request to bind9, and it worked fine. We got a response to our authoritative name server, and we got a request to the authoritative name server, and we got a response. Means we can use 8-bit bytes, which means it makes our tunnel 60% faster, or we could put more data in our data request, to be precise. Now, this was bind9. The thing is, not all software has to have allow binary requests. So we tested a couple of them, found out bind9 does allow it. So does GJ DNS. Not all allow it though. Do we have any Microsoft people here? Yeah. Well, the Microsoft DNS server did not allow it as such. We could send a request which would be forwarded to our name server. But in the response, which of course uses the same host name, we would get forwarded a server failure, so the response doesn't go through, which is not a big problem because we still have upstream data, and we can do something against the downstream data. We can receive the downstream data differently, so this is not a big problem. Even with Microsoft domain main server, it would work, which is a nice thing. Yeah, as I said, we will see that through the presentation. Now this is upstream data. How does it look downstream? Iodine implements null queries. It would request a null query which can contain arbitrary binary data already. The problem with the null query is it's marked as experimental, so we can use it, but it's not a good thing, or we shouldn't rely on it because some softwares might not have implemented some servers. Hence, we would like to fall back on TXT requests, which should be implemented standard anyway. Now we did some tests with TXT as well and found out that TXT can also contain arbitrary binary data, which means that in the end, our tunnel or our data is 33% more than actually expected what it was before. We only allowed A to Z, which is case sensitive in this case, so we would encode it base 64. Now we don't have to do that anymore. Yeah, this is how we would make it faster. Now the stealthy part, please.
Now the stealth part, so again, we have a slightly faster tunnel. The problem again is that our agent will create this massive amount of traffic, DNS traffic. If we map the DNS request per minute on a y-axis and an IP address on an x, we will see that probably we will have some guy in there performing a massive amount of requests. Any anomaly-based IDS is very likely to notice something like that. So the idea was, okay, how can we take the same amount of traffic and spread it all over the network segment? How about spoofing? I mean, we are dealing with DNS. DNS requests are usually performed over UDP, except, well, zone transfer, unless you really decide that you want to use TCP. But we can use UDP. With UDP, we don't have to mess with sequence number. We don't have to do any guessing work. We can just easily spoof packets using each time a different IP addresses belonging to the same network. Of course, this is not like bulletproof. There are modern switches. They all provide some kind of per port level of protection that is able to figure out whether the spoofed traffic is coming from there. But again, in our experience, only the most paranoid administrator actually enable this kind of protections. Since we already messing up with our packets quite a lot in order to shove binary data into them, it's not a big deal at this point just to mess a little bit more and just change the source IP address. The problem with that is that, okay, the DNS request is spoofed and it will definitely, very likely reach our host. The problem is that our host will send out a response to the DNS server, which will try to deliver to the spoofed IP address, and also which means that our agent is not able to receive the response. And that would mean that we are limited to a half duplex channel. However, what we did was to split the tunnel in two. We create two concurrent communication channels. The first one uses spoofed packets to transfer upstream data. So you see that the data up is sent with spoofed packets to the DNS server up to our box. The response go back to some other IP address for instance, NX domain response. And a second channel which uses unspoofed requests, and that we'll see why, without any data encoded in it, and just wait for the responses, which will contain the downstream data. So basically, we have two channels. One takes care of transferring the data out, and the other actually takes care of bringing the data back in. The fact that unspoofed query do not need to send data solves the issue with server failure message. If there is a Windows DNS server in there, we use binary data. We don't care at that point to receive the responses. We will receive the responses with the non-spoofed packets will not contain any data, so there won't be any server failure, and we'll safely retrieve our data. So that's pretty much how the tunnel looks like. The colors are not very good as they're supposed to be, but basically, yeah, you have the box in between, which is the box with the agent. All the upstream data appears to come from all the other boxes, is delivered to our box, which actually sends data back using the responses to the unspoofed requests. A bit of analysis here. I mean, the problem with this approach is that we overall need more packets. If we think about a perfectly symmetric channel, which means the same amount of traffic, same amount of data that needs to be transferred both way, same amount of number of packets. I mean, we need to double the amount of traffic because we are actually creating two completely separated channels. The only advantage would be that, yeah, the requests are, with this weird binary hostname, are actually spread across the whole network. It would make our tunnel a little bit harder to detect. But again, we would create this, would double the traffic. However, the point is that DNS tunnels tend to be quite asymmetric, which pretty much solves our problem. First of all, we have more space in the responses than in the request. Just using plain normal DNS messages, for instance, on TXT we have 256 bytes. If we use ADNS0, which was defined in RFC 2671 to allow a larger DNS message, we have even more space. This means that even if the data transfer is symmetric, so same amount of data in both directions, we might only need one response every circa 4 requests, but that's not all. If you want, for instance, an RDP session, you're going to have a lot of data to send out. You're going to have all the graphics, all windows, the whole screen that you need to deliver on the other end. Whereas downstream, you only have mouse events, clicks, keystrokes. You have very little data that you need to send. In a real RDP session, for instance, the downstream data, the upstream data is actually 6 to 7 times the downstream data. So it also means that it's actually we get quite a good advantage to actually spread the upstream data. And things are even better in a corporate espionage case, in which all data is upstream. You can send out like terabytes of stuff, and on the other direction, you probably just need to send the hash value just to check that the transfer was successful. Other than that, you can do everything with the spoofed request. So actually, splitting and spoofing, it's actually quite convenient if you're dealing with the proper kind of data transfer. And new traffic signature could probably be something like that. There might still be a little bit of a peak with of the infected host, because of course there is still the unspoofed requests that need to go out, but there will be a very limited amount of them. All the rest will be spread across the whole network. The overall area that is identified by all those lines will be slightly larger. There will be like a larger amount of DNS requests, but an IDS would probably not notice that too much unless it's really a massive amount. Everything is spread across the whole segment. Regarding the responses, there are actually 2 possible approaches here. Sending an NX domain to spoof request is not very necessary at this point, because of course you're not transferring any data back. But there are 2 advantages in doing that. First of all, if you have a stateful firewall in between, the stateful firewall will not see too many like half-open connections. The firewall will see that, yeah, there's been a lot of requests, but there's also been a lot of responses. It doesn't start filling up the connection table, which is good. Also, since we are responding to the DNS server of the network, sending an X domain, we make sure that the DNS will not start sending and resending the request in order to try to complete it, which means that overall will not create user's traffic. Obviously, if you send an X domain to a host that hasn't requested any DNS data, that might trigger an ICMP port unreachable. But nowadays, most client machines have a personal firewall that very often just don't answer to unsolicited data. So even if you get a DNS packet over there, it might just drop it silently without creating ICMP responses. And that's pretty much the basic concepts that we came through, and we started building up a tool to actually implement it. And we ran out into a few problems. So if you want to, here's a problem solver.
Yeah, implementation. First of all, it's not the first thing we did, but something along the way. We picked a name for our tool, which is the little blue icon up there, which is supposed to be a head of a Native American. It's called Heyoka. Heyoka is a sacred clown of the Native American culture, and he does everything differently in a way that it's not supposed to be. For instance, he would ride on a horse backwards, or he would wear clothes the other way around. And that actually quite fits to our tool because we use DNS in a way it's not supposed to. And we cause a lot of weird traffic probably in the network, or we can cause a lot of traffic, weird traffic in the network, and that's why we picked that name. At the moment, the Heyoka, the tool, is quite beta. It works. It works good as well. It's not very user-friendly when it does work, at least. And we had a lot of problems along the way. For instance, problem number one, of course, UDP is not reliable. Packets might not arrive. Packets might arrive in a different order, and all these things. Probably the biggest problem we had to do something against it. We had to keep trace of a packet. We have to detect when a packet was lost, and well, in order to do that, basically, we can send control data in every packet. For instance, we could send, we could tell the authoritative name server or the client, basically, I received those packets, or I'm missing these packets. And the way we did it, we implemented sequence numbers and acknowledgement numbers. In every packet we send out, we send a sequence number, and next packet would be sequence number +1, and so forth. The other endpoint would then send in a response the acknowledgement number, the acknowledgement number of the last packet you received, and that's way we can control which packet we received and which we haven't received. The problem with that is there's not much data, not much space in the request, 250 bytes approximately. We want to keep it short, hence we pick 2 bytes for sequence numbers and 2 bytes for acknowledgement numbers. It is sufficient, actually, 2 bytes. It's probably too much, and we could even go less, but surely not more. This is probably familiar to you. It's basically what TCP does, and we implemented it ultra squeezed for UDP. Yeah, problem number 2, the spoof packets. The master, our authoritative name server, will receive a packet from another name server. And from just the packet, you couldn't tell whether this was a spoofed packet from the internal network or if it wasn't. So at this point, the master should actually make a decision whether to send back data or just an X domain or some other arbitrary things. So what we did to add to our sequence number and acknowledgement number, we add a flag saying this is a spoofed packet or this is not a spoofed packet. And the server then, the master would pick up this flag and then decide, do I send data or do I not send data? The encoding, as said before, we can send binary queries or queries with binary data, which should work for most of the name servers. But it might be that some of those name servers actually don't support this, and then we run into trouble if we only have that method implemented. So what we basically want to do is to fall back on base 32 in case our binary did not work, which means basically we have we have 4 combinations. From the slave to the master, we can either send binary, which is great, or fall back to base 32, which is, it works, it's just a bit slower. From the master to the slave, we have either binary as well, or base 64, which is 4 possible combinations. And in order to now negotiate which one we're going to use, we have to send a couple of initial packets, which we call the handshake. Looks like this. The slave would start at some point sending a data sample, which at the beginning is plain text data, binary, sending to the master. The master would pick up the data received, put it in the response, and send it back. The slave hopefully then receives this packet, well, either receives it or not. When he receives it, he would get the data out of the response and compare it with what he sent off. If that is similar, or if it's exactly the same, this means this would work, the encoding binary in the request, binary in the response. If the packet does not arrive or the data is different, it means something is wrong. So we're going to try the next encoding, which would probably be binary in the request and base 64 in the response or something similar. At some point, we either get what we want. We have a encoding which we can use, or not at all, which means we're going to use the next name server and not bother with this one anymore. Yeah. Well, having a handshake means we have actually 2 different kind of packets, a handshake packet and data packets. So we have to signalize to the master again, this is a handshake packet, please send handshake response to it and don't send any data, which means another flag, 2 bits now for our flags. Doesn't make it much worse, actually. Now, back to the encoding. The most internal network, or most networks generally have more than one name server, a primary and a secondary name server, maybe more. And it would be nice if we actually could use all of them to tunnel data out, which means we can actually balance the load between them, and we can possibly speed it up as well. Now the problem is that either different, if the same software is used on both servers or more than both servers, we might be able to use both the same encoding on both, but possibly not. Maybe one of the servers just doesn't support binary because of whatever. It's an older version. It's maybe a different software in use. So what we want to do is, during our handshake, actually, we want to test each of the name servers with different encoding. And then we have a list of name servers and a list of encoding which work for each name server. And at that point, it basically means that we're going to need something else in our in our header structure from before. But first of all, using more servers, as I said, we get more bandwidth out of it. The tunnel is possibly more difficult to detect, because if you just look at one server, you don't see much more data going off that server. But if you see them in the combination, maybe. Also, if one of the servers fails, we still run our tunnel, because we can still fall back on the other servers which are available. As I said, we need more in our header, in our control header, which now looks like this. We're going to have a flag, which is the first character, the first byte, if you want. But we call it character because it's actually a base 32 character. We're always going to encode it base 32, which means we have 5 bits. We encoded base 32 because this is an agreement, basically. Base 32 always works, and the master would always pick the first byte and say, oh, this is base 32 decoded, and get his flags out of it. We now have a flag for packed spoofed packets, for the handshake, and for the encoding from the slave to the master and from the master to the slave. And after that, everything is encoded in a way it was specified in the flags. Using multiple slaves, that would be nice, actually. If we go back, sorry, if we go back to the corporate spy thing, or generally Trojans, probably you're going to infect a lot of machines. You want to, in the end, you want to control all of them. So they should contact your master, which means the master has to know which slave is contacting him, and has to send a response. This is not a difficult thing to do. You can either use a different subdomain for each slave and identify which one is which, or you can do it more convenient and we introduce a ticket, which is just a byte, so we can have, at the moment, 256 slaves, and every slave would get one ticket, a unique ticket, of course. The problem is slaves do not know which is a unique ticket, so in the handshake, the first request would not contain any ticket, then the master would assign a unique ticket, and from that point on, slaves use unique tickets. And this is our control header in just 6 bytes, I think, which is a good thing. So we have a lot of reasonable amount of space which we can use for actually payload. This is usually, well, this is all upstream though. This is from slave to master in most cases. The master now might want to tell the slave a couple of things. Well, first of all, actually, from the master to the slave, we have more space in our flag if we take the first byte. If the first byte, which is our flag, we could encode it base 64, always works in TXT because. But we're lazy and we don't need that much space, so we use base 32 there as well. But this is just something implementation specific. It doesn't really matter in this case. The question though is if there is the master only responds to requests because it's DNS. So we send a request, master responds, but he couldn't possibly send a response without a request, which means we have 2 choices basically. Either we send a lot of requests from the slave and hope that there's data coming back, or we send just occasionally a request and maybe some data is coming back then. The problem now is if we have a lot of data on master side, we would like to have a lot more requests coming from the slave because we want to get rid of our data from the master. If we don't have that much data on the master side, we just want occasionally a request when we get more data. So what we do is from master to slave a more data flag. If there is more data waiting, if there's more data waiting, we flip a flag and tell the slave, okay, please send another request now. And this is basically how it looks like. We call it a heartbeat. The slave, by default, would send a request, an unspoofed request, of course, every 500 milliseconds. If the response he received last has the more data flag set, he would immediately send another request and get more data of the slave, of the master. So if that flag is not set, he would just wait another 500 milliseconds and then send a request, which is it's adaptive timing. We make our tunnel very dynamic, and we can control the amount of requests basically sent. And I think it would be nice if we could show that then.
It would be nice if it works.
Yeah.
So now praying to the demo gods. A possible exploitation scenario. Let's say that you have found a SQL injection on a web application, let's say with Microsoft SQL Server's backend, just for pretty example purposes. Let's say that you have SA privileges, or you've been able to escalate privileges. Let's say using open row sets on SQL Server 2000, or you've been able to exploit a heap overflow on SP reply write to varbean. You manage to get SA privileges, you enable XP command shell using SP configure. You enable RDP if it's not enabled already. You add a user in order to be able to connect to the RDP, upload a Heyoka.exe, and just run it. One point here, okay, how can you upload stuff if you don't have any direct communication yet with the machine? Which is why I chose this example. It's very easy to upload executable and run them through SQL injection in a scenario like the one I described. For instance, any executable up to 64Ks can be represented as a script for the Windows, the old MS-DOS debugger, which is still shipped by default with old Windows version. So what we can do is actually translate Heyoka.exe to this debug script, which is going to be a txt file. Then using an XP command shell and echo, just recreate this file on the target database server, call debug.exe on it, and debug.exe will recreate the executable. It's very easy to do. There are tools that actually do that for you automatically. If a file is larger than 64Ks, we can just split it in chunks and then use copy /b in order to glue them together at the end. Alternatively, we can just encode it in some way. For instance, you encoding them, and then upload a small VB script that will recreate the original executable. And finally, regarding how to add the user and enable RDP, it's very easy using XP command shell and XP rec write. XP rec write is an undocumented extended procedure that allows an administrator of a SQL server to write arbitrary data on the registry. And that's basically it now. I have a couple of virtual machines on here. Let's bear with me 1 second. And there is a vulnerable web application. So for instance, let's say there is you can retrieve products out of it. We add a single quote at the end. We have a nice SQL error, meaning that the application is vulnerable to SQL injection. So what we do now, bear with me 1 moment. I'm gonna put a sniffer here to see what's going on actually. I'm going to start the master on my machine. There is a bind server configured on the Mac OS X, which will actually relay the requests. And if I call Heyoka, that will create an RDP connection. It's not very fast. It actually can be a lot faster. Now I have my user here that I added, and I mean, the funny thing is actually it used to be faster. It was a lot faster on our testing on our local network. Using VMware Fusion networking, things get a little bit funny. So we actually artificially slow it down a little bit, ending a couple of days in the code. It can actually be faster than this in a local network. And if we go back to well, now we can play around with it easily. I mean, we are in. And if we get to the sniffer, okay, I didn't run it, but basically what we see that's changing the data here. We see that there's a whole bunch of different IPs addresses here, showing that actually the traffic is spoofed. There's also .1, but it's actually the bind server actually forwarding the requests. So that's actually why it looks like a big attractor in there. But again, we have a spoof tunnel. Everything works fine, and we have a nice graphical interface on the remote box. So let me just close it down now. Okay. Getting back on the presentation, if I can find it. Okay. Few future improvements, first of all. I mean, this is a work in progress. We have lots of ideas. I mean, this is still a beta, very user-unfriendly. We have several ideas. First of all, actually delve a little bit into DNSSEC. Is being deployed, finally. There's probably a lot of space to play with there. We also received some very nice ideas about how to abuse caches. So actually allow the internal DNS server to cache lots of the content that needs to be brought back to the slave, and then use it in order to use a cache to retrieve it. Well, it needs a big major code refactoring. Running the tool through Fortify right now would not produce a green flag. At the moment, it only works on Windows, where we're planning to port it to other platform, and also create some APIs so that it can be easily extended, for instance, using encryption, a decent GUI, and then hopefully an official release. A few takeaways. Forbidding your host to establish connection to the internet does not mean that they're not communicating with the external world right now. As we have seen, there are a lot of methods that can be used in order to have two machines exchange some bit of information with each other. And a determined attacker can find lots of ways, can be very inventive with that. We use DNS. Other protocols can be used as well. Again, this is just an example. There's plenty of other ways to do it. And which means that in the end, protecting data against data exfiltration is a hard job, unless you want to get rid of TCP IP altogether and implement a unidirectional networks. But unless you're in the military, it's quite unlikely that you'll do that. However, in the meantime, be sure that, well, do not allow hosts to resolve external names, and try using an authenticated proxy for all communications. Everything going from the inside to the outside needs to be authenticated and go through a third trusted machine. And finally, modern switches provide port-level anti-spoofing protection, so use it. Few credits. Dan Kaminsky and Christian Ryuk, which I see back there, have been very helpful in giving us idea and doing some peer review. Other people contributed as well. Bernardo D'Amelia, the creator of SQL Map, kindly provided us with an SMS server to avoid losing our data with every system crash. And we had a lot of moral support from Ethanol. And that's basically it. Again, this is going to be published on heyoka.sourceforge.net. At the moment, it's not public yet. Again, we need major work. But if you want like a beta version, you want to see the code, play with it, just come through us after the talk. We're happy to share the code. And don't be too evil finding bugs in there. We know there's a lot. But if you want to play that with that, it's fine. And if you have any other information, want to contact us, these are details. And any question?
Yeah, when you lose packets because of UDP, how do you get it to retransmit? Because you can't get back to
The master uses the acknowledgement number. Also, from the master to the slave, there's going to be a sequence number and the acknowledgement number. And the master will tell the slave up to which packet you successfully received packet. And there's a window after that. The slave will resend packet up to the last acknowledgement number plus 64 at the moment, I think it is. And if this window is filled at the moment, it will start resending back the packets that were lost. So both sides actually buffer all the packets that haven't been acknowledged yet and resend them if necessary. So yeah, it's a little bit flaky compared to like the full TCP implementation, but it works quite well, quite surprisingly actually. We were quite happy to see with such a tiny control protocol, things are quite reliable. Wow, only one question. We must have been quite clear.
So
okay, cool.
Test engagements, are you already using this?
Sorry?
Are you already using this in your pen test engagements?
No. This is a very preliminary version. We still haven't tried it on a field. I tried a couple of other DNS tunneling, for instance, SQL Ninja. I used it in a couple of engagements. It worked fine. But no, this hasn't been used in the wild yet. We'll let you know if the first time we do and how it works. I mean, the point is also, I mean, from a penetration testing point of view, it's quite unlikely that you will need to actually have spoofed traffic back. You're not very likely to need such a covert approach, such a sneaky way to exfiltrate data, unless the client specifically asks you to be extremely stealthy for IDS or IPS. So I don't think it's more for a pen tester, rather trying to show that it's possible actually to do this spoofing thing and try to raise awareness on the risks of allowing internal hosts to contact external DNS servers. My point here is more trying to understand that whether it's possible, and yes, show it is, and so be careful in your networks how you configure your internal hosts, how they resolve external host names. But yeah, we'll definitely give it a try as soon as we have the chance and when it's stable enough. Anything else? Okay, that's basically it. I think it's break time.